So we're shifting from heads inside the gray box to talk about probabilistic views of these systems. You might imagine this is the perspective of an observer who comes to a new system and just has data and it looks kind of noisy and probabilistic. So the first blush is that would be the set of tools you would first appeal to. Notions from probability theory, measures of randomness, and so on. So what we're going to do is 3 lectures, nominally on trying to understand how to deal with stochasticity. The first will be a little bit, today will be a little bit looking back at dynamical systems and trying to understand how dynamical systems evolve probability distributions. In a sense, today, I'll introduce some new terminology, things like that, because we have a new set of ideas from probability theory. But the basic idea is very close to what we've already seen in dot spreading, right? You could think of that initial cluster of 100,000 points on the Lorenz as some kind of pointillistic summary of a very tight probability distribution. And we saw the net effect was to take that and stretch it out and spread out the states. So we'll formalize that today and then look at some simpler systems, namely one-dimensional maps and how they interact with probability distributions. But the idea is not really so different from that. So that's fine. So we'll look at how dynamical systems operate on probability distributions and introduce a few key ideas from probability theory that are appropriate for understanding that. But we're also interested in trajectories, orbits over time, and eventually measurement sequences. So not so much today, we'll be looking at the state space and a distribution over states. We're interested in the appearance of stochasticity and randomness over time. And up to this point, we've been talking about chaotic systems having really complicated orbit sets. So there's a corresponding set of questions looking at these complicated behaviors as a stochastic process that unfolds over time. And then sort of the final step in this is to acknowledge the fact that our view of the world, the way we interact with it, is always is mediated through some sensory apparatus or through some instrument in an experiment. So we'll introduce ideas of measurement theory, which are important. Why do that? Well, again, kind of appealing to the dot spreading experiment, we could think of that initial tight distribution was the limit of our experimental control of the initial state of a system. There was a finite resolution. And we saw the consequence of that. If I couldn't exactly control the state of a system, small variations beyond my control, beyond my measuring instrument's ability to distinguish, actually got manifest in the macroscopic scale. And then this will set us up to start talking about how to describe stochastic processes using information theory. And there'll be kind of another sort of punctuation point here. We'll kind of step back and ramp up again basic ideas in information theory. Just like these 3 lectures, we're kind of resetting a little bit and starting with some new ideas from probability theory, ramping up. Okay, so just to emphasize, we've had our heads inside the gray box here. In a sense, we get to do that today too, but soon we're going to close the box. And the goal is to be down there where observers are building models. Actual model building won't happen until the spring quarter, but we're going to talk about instrumentation, notions of stochasticity, and then information theory. And we're going to pretty much exhaust what information theory has to say about the modeling process. And then we have to do something else, and that'll be spring. So we've been here, and we're pretty rapidly moving to here, namely looking at stochastic processes. Again, the reason we study dynamical systems, I wanted to give you a concrete sense of how systems can produce noisy-looking, random-looking behavior, even if they're deterministic. There are other sources of noise in the world. Inaccurate measuring instruments, maybe our measuring instruments or sensory apparatus itself is noisy, introduces some noise. Maybe we don't have the right conception of the world, right? We think the planets are moving in terms of epicycles. So we have this very complicated, essentially periodic decomposition of the motions, but then suddenly, Mercury goes into retrograde, and like, uh-oh, that's not regular periodic behavior. So the system appears more complicated in that view until we humans decide that maybe it's a better model to have the sun at the center and have the planets orbiting around, and suddenly we have these nice elliptic orbits that are easier to describe and also to predict other behavior. So there are many different levels in which there's uncertainty. The world appears uncertain to us. Deterministic chaos is this one active mechanism, but there are also issues having to do with resolution and accuracy that an observer observes the world with, but also even sort of cognitive or conceptual bases that are wrong. In fact, in that case, you could say, will the data ever tell us how a system itself should be represented? So again, more advertisement for the spring. We'll finally have enough tools that in spring we start to answer some of these bigger questions. Okay. So first few things, or just definitional, just to kind of remind you of some of the ideas in probability theory. This is not in sufficient detail that if you don't know probability theory, you can sort of ramp up from it. But you can go look at pretty much any, I'd say maybe junior, senior, college level probability theory or stochastic process text and read a first chapter or two. The classic reference in probability theory is Feller. And it's the 2-volume set, one of those, gold letter embossed, gray bound volumes. Suggested readings are on the one of the pages on the class website for this. We won't need a lot of detailed probability theory because we're going to adapt it to some particular uses. Okay, so just to get started here, 2 cases, discrete case and continuous case. So we're going to denote a discrete random variable, capital letters, typically X and Y and Z. And then the idea is that as we look at the system, events occur, so-called events. And then those events are labeled out of some alphabet. Could be K different events, could be rainy, not rainy, could be sunny, not sunny, could be heads and tails. But there's some finite set of events. And we talk about the random variable having a, quote, realization. I'm looking at the coin, and I see that it's heads. And so the notation here is lowercase symbols mean a particular value. Right? So the realizations are one of these labels. At some particular moment, you look at the system and it's tails. So that's lowercase. Now, okay, so that's just the variables we're looking at. We've chosen these observables. Now, how are we going to describe the probabilistic aspect? Well, for discrete random variables, there's just sort of one object called probability mass function. Sometimes we'll use the word distribution. In the discrete case, that's not a confusion. And what we mean here is that when the random variable takes on a particular realization, there's a number associated with that called its probability, the likelihood that this thing occurred. And we'll just denote that this way. I tend to be a little more verbose because I actually think probability is a very sophisticated concept. So I give it some more ink here. I say PR to mean probability. So the shorthand for the probability of heads or tails occurring would be probability of X, like that. And you'll see in some probability theory texts, in some context, especially in more mathematical settings, sometimes you actually have to write out this more verbose notation, the random variable taking on this value. But shorthand is fine for us. Now, what are these numbers? Well, they're between 0 and 1 inclusive for every event. And when you sum them up, they're normalized. Okay, that's fine. What does normalization mean? It means that something will always occur. Even if one thing and only one thing occurs, it must occur with probability 1. So that's what normalization means. Examples? Well, okay, a biased coin. The event space is over heads, tails. This is the alphabet, HT. And then to specify it, we have to give the probability of the random variable capital X being heads, probably 1/3, being tails, probably 2/3. Numbers between 0 and 1, and they sum to 1. Normalized distribution. Another kind of random variable would have this event space. This process emits sequences of blocks of 3 bits, three binary variables. There are 8 possible, so the event space here There are 8 binary strings of length 3. And here's one particular example, random variable, where I assign probability 0 to 3 zeros, 0, 0, 1, and 1, 0, 0. I could describe this random variable as no pairs of zeros, if you like, some narrative description of that. And then 1, 0, 1, probably 1/3, and all the others have probably 1/6. So you have to go through here. These are probably 0, so I've got 5 other events. That's got 1/3. These others have these 4 other events, probably 1/6. Well, that's 2/3 plus 1/3 is 1, so it's normalized. And so on. Okay, just a little definition, mostly introducing terminology and a couple examples. The other kind of random variable we'll look at are continuous random variables. Same notation here. Capital X is the random variable. Now our event space is continuous. Think the real line. And we have 2 different ways of specifying the probability of events. In fact, when we have a continuous event space, it's a bit of an issue what an event is. If I say X takes on the value 1/pi, that's a very specific event. In fact, it's so specific, that particular thing will never occur under most distributions. So as a consequence of that issue, there are 2 ways to talk about probability over continuous random variables. One is the cumulative distribution function. And what that is, it's the probability that the random variable takes on a value up to some particular realization value, little x. Okay, I'll just note that p of x there. Again, these numbers here are between 0 and 1. So this function goes from 0 to 1. And we also say that if this function is continuous, so now you kind of imagine this is a function of x, and we're moving x along its domain, and it's monotonically increasing. We're encompassing more and more of the event space, therefore these sets of events only get more likely. Then we say the random variable is continuous. And I'll show you some examples of this. Probably what's more familiar and resonates more directly with the notion of probability for the discrete variable case is the probability density function. Crudely speaking, the probability density function is like the derivative of the cumulative distribution function. So it's a positive number. And we're thinking now of the probability of a small infinitesimal range about the value x. So the way we think about this is actually define it this way. This is just a sort of metaphorical description as a derivative. What we do is little p of x here, it's probability per unit interval. That's why it's called the density. And it's the difference between the cumulative distribution function. Probably that x is less than little x plus dx minus probability that the random variable is less than x. So there's some small little interval of change. Normalization has 2 different expressions here. One for the cumulative distribution function, the probability that x is less than infinity, basically the whole continuous event space, is 1. Something has to happen. Something happened. Or we can integrate this probability density function over the domain, over the values of the continuous random variable, and that integral should be 1. So here I'm writing these down not in sort of the general case, but as if the realizations were on the real line. One useful notion, which also applies to discrete distributions, if I give you a random variable and its distribution, sometimes we're interested in the support of the random variable, and those are simply the events, the realization values, the events that have positive probability. Okay, just definitions here. Examples, hopefully will help clarify this notion of the difference between a density and distribution. Continuous random variable x, let's take the realizations to be the real line, so just one-dimensional random variable on the real line. And this one is just going to be uniform distribution on the unit interval. So that means that for the probability density, which I find more intuitive, we have probability 1 when the random variable is between 0 and 1, and it's 0 otherwise. So you can imagine in your mind, the plot is 0 everywhere except on 0 to 1. We have this function which has amplitude 1 between 0 and 1. Now the distribution function, again, this is the probability that the random variable takes values up to the value x. So that's 0 for x negative, right? There has been no probability. It's actually a linear function on the interval, and then it tops out at 1 for values, for realizations with value larger than 1. Right, so that plot goes like this and then levels off. So you can see how this is like a derivative, right? The distribution function had constant slope. This had constant value over the interval. Okay. And then finally, the support of this random variable is just a unit interval 0, 1 inclusive. Another familiar one, example of continuous random variable on the real line here would be the Gaussian distribution. The density is what we usually write down. That's what we work with. That's just this familiar exponential quadratic form with mean and standard deviation. Now, the cumulative distribution function is this kind of complicated object. I want to know what the probability that x is less than this value x. I integrate that from minus infinity up to the value I'm interested in over the density, which integral one cannot do in closed form, but it happens so often that it's given a name. It's called the error function. And this kind of highlights a little bit why often it's more intuitive to work with densities. But there are some problems that come up with very complicated distributions and densities, which we're going to run into. Our dynamical systems are actually going to generate really complicated looking densities where sometimes the distribution, this integral form, is easier to work with. But okay, familiar examples. Very often we have sets of different events out there, different observables, and we have questions about how they're correlated. This could be measurements across time, or it could be two different variables, temperature and amount of sunlight. So we need to talk a little bit about sets of random variables. So we're going to have two, big X and big Y, and they'll have the corresponding alphabets, script X and script Y. And they're going to be described by what's called the joint distribution. So we can think of now the notion of event are pairs of occurrences of X and Y. And then we assign probabilities just like we did before. Okay. We can recover, if we were just interested in the distribution over X, we can recover what's called the marginal distribution by summing out all those values that Y can take on, the particular values. This is a normalized distribution. It's a little bit of an exercise to show if I have a normalized joint distribution, the marginals are normalized. It's pretty straightforward. Then we can also project down or marginalize down to Y by summing out over all the realizations of random variable X. Well, that's fine. We just took the previous notions and generalized them to pairs. Now, slightly more interesting is to talk about how if we have this probability distribution over joint events x, y, how we can factor that function in different ways. So here, what you can do is we'll talk about what are called conditional distributions. I'm sure this is familiar to many of you, but stay tuned. It will get complicated in just a little bit. So we have the probability of x and y, and we can factor that into the product of the probability of x given that we know y times the probability of y. We also have another choice, same joint distribution, probability of x and y, but now I can factor that into a conditional distribution, probability of y given x times the probability of x. And this move, this choice that you can make, is used over and over and over again. Maybe most famously, it's called Bayes' theorem in inference. So, you just have a choice here. And comparing and contrasting the two different factorizations often leads to interesting results. So what are these funny things here? These conditional just probability of x given y, probability of y given x. Well, they're essentially defined as the ratio of the probability of the joint distribution over the marginal. So probability of y given x is probability of the joint or probability of x. Obviously, we can only do this, and it's only well defined when the x events occur with some probability. So we have to be a little bit careful here. It doesn't make sense to say, whoa, what's my uncertainty in y given x if x never occurs. So there's a little bit of subtlety here. We'll work in examples where this is issues easy to take care of, but this definition highlights a little bit of what is going on behind the scenes and why you have to be a little bit careful. A very common question is, if I have two variables x and y, is how are they related? And I would say almost all of the information theory we're going to develop is to help us be more explicit and quantitative about how variables relate to one another. In the context of probability theory, we have this notion of statistical independence. So we say that x is independent of y with this upside down t here. And what that means is that this joint factoring is just simply the product of the marginals. Right? So think back to the previous definition of conditional distribution. Our uncertainty in x and our uncertainty in y aren't conditional at all. The probability that the event x and y occurs is the product of probability that x occurred alone and the probability that y occurred alone, just their product. So this is one way of testing. If I have some distribution over pairs of events, I can check numerically if this equality holds and then conclude that the two events, whatever they are, don't depend on each other, are independent. A slightly enriched version of this is called conditional independence. So now we're asking about, is x independent of y given some other knowledge, call that random variable z. So it's just a generalization of this. We say that x and y are independent given z if this joint conditional distribution factors into the product of the marginal uncertainty given z for x and marginal uncertainty of y given z. So there's a whole calculus of, once you introduce conditional and joint distributions, of how you can take, imagine we had 6 random variables here, and we had 2 things knowledge we had. We wanted to understand, given that knowledge, what the relationships were with the other 6 variables, the ways of factoring these things and testing independence. And we will do this again and again and again. Hidden behind this conditional independence is a lot of how we are going to talk about the structure of the behavior in random variables. We're going to try to find z's such that these other variables, we're kind of inventing these things such that it makes the observations independent. And those z's that we find that do this will be particularly informative about how the system is structured. So this might seem a little innocuous, but it's kind of the key idea that is going to run through most of the spring. So at this point, we're just introducing some notation. So this kind of this little calculus of probabilities and factoring joint and conditional joint distributions. Okay, so that's really just introducing some notation from probability theory. And now let's take a look at how dynamical systems evolve distributions. So again, the way we'll think about it a little bit is the picture of the dot spreading experiments. So we have some dynamical system now with the state space. That's going to be our event space, and then some dynamic on that space. Okay. We'll have a state density. This is just a distribution over the state space. Probably a density function over the state space. And what we've been doing so far, including that demonstration of dot spreading, was we were just choosing particular initial conditions and evolving them forward. We talked about initial conditions and trajectories or orbits that were produced. Now we're going to ask a a similar question, except for a different kind of object, not points in the state space, but for distributions. So we're going to start with some initial density, so I'll make the subscript here be time. So at time 0, we have this initial density. We specify, again, as I said for the dot spreading experiments, think of this as, could be a tight little Gaussian distribution that was some model of our control or measurement accuracy in an experiment. Could also be other things too. So how do we evolve a density? We know how to evolve points. We just look at the dynamic and follow the arrows or apply the function to the discrete time mapping. But how do we take an initial distribution and move it forward under the dynamic to produce the distribution at the next time or next instant? So that's the question here. We saw that, so we understand it intuitively, but how are we going to describe that mathematically? Well, the main idea just relies on conservation of probability. So let me describe this to you graphically first, and then I'll go through the notation. The goal here is to generalize the dynamic that we have that takes states to states to a function that operates, a dynamic that operates on distributions. Okay, so first step is we assume conservation of probability over time. So here I've got some, just think of this as if it were, say, a discrete time mapping. This will be the sort of initial state and the state at the next time, and then I have some function, call it t of x here. And the question here is I have a little bit of probability mass, and that's situated between x and x plus dx. The yellow area here corresponds to the amount of that probability mass. Right, so I have the density function times the little dx. Density function is the height times dx, and that gives me an area. That's a probability number. That's the probability that I will find the system between x and x plus dx. And now I'm going to push it forward through t of x. And I'm assuming that probability is conserved. What that means here is that the amount of yellow here is the same as yellow here. So now in this cartoon picture, let me just say something about how you should be thinking about it. Imagine I'm down here and I have like a little coordinate axis as x and probability of x down here. Think of that up here. In this direction, I have probability of y in the y coordinate. But graphically, what happens is this yellow amount comes up here and it's the same. So we know how to take x and map it forward. So x goes to t of x, which is the variable y. X plus dx, put that into t of x and get y plus dy, that's up here. And then, for example, if this distance here shrunk because the slope was low, the distance between y and y plus dy would be small. And so that I had the same amount of probability mass, the amplitude, p of y, would be larger. Also the converse, if the slope was very, very steep here, this interval, the support, is going to get spread out. And in order to have the same area, then the probability amplitudes in the next step would be less. Okay, so this is what I just said. I'm mapping forward a little bit of the probability density function. At the next time step, I assume I have the same amount of probability in that little area. Right? Yeah.
How does that deal with, say, functions are like single value?
We'll get to that. Yes. Stay tuned. Next slide.
Next slide.
Yes. Well, in fact, maybe I'll even say it down here. Yeah, here, this slide. Right. So again, probability density times the dx, that's a probability number. Think of it as an area. Same thing here. Density times the dy, that's a number. Those are equal. Yellow is equal. Okay. So that's the idea. So how are we going to describe this mathematically? Well, we want to think about some operator that takes the current distribution to the next distribution. So that's the first way to do this is called the Perron-Frobenius operator. And so now we've got locally, we have our function t of x. And what we want is the distribution in the range of t of x mapping from its domain. So what we're going to do here is basically just formalize what I said in terms of the slope. So the probability amplitude, so I'm calculating this height here, okay, at the next time step. It's the previous height divided by the absolute value of the slope. Okay, first, y absolute value? I don't really care whether it's a positive slope or a negative slope. What I'm interested in is how much that little dx got stretched out if the slope was greater than 1 or shrunk if the slope was less than 1. So we do that by putting the slope in the denominator, right? So as the slope goes to 0, whatever probability mass I have here is getting concentrated in a smaller and smaller interval, which means all that mass gets piled into it, and therefore I have very high probability. The probability concentrates when the slope goes to 0. Then we're dividing by a very small number, which means this on the left-hand side gets large, and vice versa. If the slope is very steep, small variation here gets spread out over the whole thing, and then that will reduce. This will be a number greater than 1, and therefore the probability amplitude at the next time in the range of the function will be less. The amplitude will be less. Should sound a little bit like kind of stretching and shrinking we were talking about before. Now, this is just a local view. So just like you were saying, there might be other contributions. Imagine t of x dip down over here. So the way we think about this, and this is kind of the main idea of evolving the probability distribution forward, the curious thing is the way we think about it is we look at the range of the function and we ask, who contributed to me? Because we're mapping forward, okay? So that's what this is. So I'm just taking this, heuristically described dependence on the absolute value of the slope, how that modifies the probability amplitudes. And then what we do is we just sum over all those values in the domain of the function, domain of t of x, that contribute to y. So this notation here means the set of x, well, the x's in the set that are the inverse images of y. So I'm sitting here and asking, oh, here's one contribution, maybe t of x is over here, we've got another contribution. Okay, so this is the Perron-Frobenius operated way of thinking about it. The cleverer and more analytic way of doing this is called the Frobenius-Perron equation, and this is the actual operator we'll use. So let me kind of explain the equation first, and then I'll describe it graphically how it's working. It's very clever. So what do we have? So we're starting with a distribution at time n. And we have this mapping, t of x, that's going to push it forward to time n plus 1. So we want this probability density function over the range variable, y. And to get it, we integrate along the domain variable of the function t. And as we're doing that, we multiply the initial density. These are the masses that we're moving, the amplitudes we're mapping forward, against this thing called the delta function. So let me explain what this does. So the delta function here we've got y minus t of x. The delta function is actually transforming, we're sort of moving along in x, we're integrating. Then we're mapping that forward to the y value that t takes it to, and then this delta function sort of samples this distribution where y is equal to t of x. So generally, the way this delta function works, and one should do this carefully, but here's the intuition. The delta function, you can think about it, it's as if it's a distribution function. It's going to sample, it's going to be peaked. Delta of x is infinite, where its argument is 0, and it's 0 everywhere else. It's really just a mathematical trick. So I'm formally defining what this thing is. It's actually normalized. It's defined to be normalized. So if I integrate over the whole domain x, delta x, I get 1 out. So it's a little bit odd. I've got this thing that just exactly 1 point where its argument goes to 0, it spikes. But we're going to use it to sample our distribution here. And the key property is that when I integrate a delta function against a function, some arbitrary function, f of x, it returns, when I integrate it, it returns the value of f of x at the value where the delta function argument went to 0. So here we have this delta function is going to be infinite when x is equal to c, and sort of samples f right there. So I get the value of f of c back out again. So you can think about these are just kind of formal definitions of what this delta function is doing. So we're just integrating, this could be, any function here, and it just samples at one value, x equal to c. I could put a couple other delta functions in here, x minus, d, x minus a, and then I get a sample of f of c, f of a, and so on. Okay, so now what's going on? So remember, the goal here is to come up with an operator that pushes a distribution forward. So what we're doing is we're integrating along. What it says, okay, we're going to integrate along x, the domain of the function. And at each point where I'm at x, where y is equal to t of x, I grab this probability amplitude and move it over here. Notice that when t is very steep, if I move at unit speed here, in a sense, y is going to be moving faster. So I'm going to take these sample probability amplitudes and spread them out, just like we did before with 1 over the slope. Or if it was slope is going to 0, if I move a lot here, y isn't going to move, so the probability masses here are getting piled up, just like we wanted before. And in addition, we automatically take care of there being values in the range of t where I get multiple contributions. So this is very clever, maybe a little bit kind of like a gimmick, but it's nice, and we can use this to calculate various things. Like, yeah?
Can you do anything about it if it's not a function, so if it has multiple y values for given x in some places?
We may be able to generalize it, but no, this has to be a function. Yeah, just some function. It doesn't, in fact, it can be discontinuous, it can be all sorts of things. So, this is general enough. Okay, so just to sort of exercise this a little bit to show how it works, let's think about a one-dimensional map. So x of n plus 1 is some function of xn. We have values on the real line. And then what we're going to do here, and this might sound a little silly, but it's a good base case to get started with. My initial distribution is going to be the system is at x0. And I represent that distribution as a delta function. Boom, just at one point, which is what we've been doing or assuming. So this is sort of more, sort of complicated it needs to be because we already understood that. If we're at x0, we're going to go to x1, x2. We just apply f to that, or t, f in this case. But let's try iterating it forward using this operator, this Frobenius-Perron equation. Okay, so the rule was the distribution after one step over the range variable y is the integral of the initial distribution times the delta of y minus f of x. Right, it's plugged in for t here. Well, what's our initial distribution? Well, it's just a spike at this one point. Okay, and so what we can remember how delta functions work. This delta function is going to sample the other function where its argument goes to 0. That's where x, the variable, the domain variable we're integrating over, where x is equal to x0. So I just substitute that in there. That's the only value that's going to be contributing. Well, what's that? That's a delta function at y minus f of x0. Well, what's f of x0? Well, that's x1 by definition. What's this? That's a distribution all concentrated at the next iterate, x1. Okay, so we just, kind of, through contortions, prove the obvious. Namely, that if we start with all of our probability on a single point, it gets pushed forward and follows along a trajectory. Okay. Well, it's a consistency check for this operator. That at least in this special case, it reduces to that. But you can see how how this works. It kind of samples, even if the other thing's a delta function, this rule still applies. So, well, okay, so that's slightly idealized. So expected. Now let's ask the dot spreading question. Let's imagine the initial distribution has some finite support, but small. So what we're going to do here is go through a series of one-dimensional maps that are sort of increasingly more complicated and show you what happens when they iterate or push forward this initial distribution. So this initial distribution, I'm giving you the density again. It's going to be uniform amplitude 20, centered around x is equal to a third, and have a width of 0.025. So pretty small, but little flat distribution there. Okay, so here's the first example which actually is familiar to us because we talked about this when we did the map lattice. It's called the linear circle map. So here it is drawn out. We have the identity here, and there's just an offset. In this particular case, just 0.1. So x0, I just add 0.1 to it, add 0.1, add 0.1, add 0.1, until it gets up to here. Then I mod 1 and wraps back around again. Okay, so now what I'm going to do is start with, so here's that initial distribution, P0, centered about a third, plus or minus 0.025, done quantitatively. The vertical coordinate, it's often helpful when you're plotting probability distributions to use log, minus log of the probability, to see the features. Otherwise, things get a bit compressed. Okay, so here we are. This is our initial distribution at time 0, and then we iterate once. And you can just tell all it really does is just move over here. There's no change in probability amplitude. So all that's really going on is where all the probability amplitudes across this little interval are just getting pushed over. We're really just changing the location of the distribution support. Okay. Not really manipulating, because the map has slope 1, it's not spreading out, shrinking, or growing the probability amplitudes. Okay. So all we get is this thing just kind of mapping around, moving by 1/10 each time until it gets up close to 1, and then it maps around again and keeps going. So we just have this distribution that's kind of just rotating around on the interval like that. So not so interesting, but it's a good comparison because we can go to the shift map. So remember, shift map is 2 times xn mod 1. So it has these 2 pieces of slope 2. Everywhere has slope 2. Okay, but same initial distribution. Now when I map forward, what happens? Well, certainly the points that are in the support of the distribution move, right? They're hopping around the interval just like iterates would. But now notice that 2 things happen. The probability amplitude has gone down. In fact, the plots are quantitative. They've actually gone down by a factor of 2. And the width of the support is now twice as big. And that's all, of course, all due to the slope being 2. If the support now is broadened, then I have the same probability mass that's got to come over here. Therefore, the probability amplitude is half what it was. And on a log scale, that's just 1 unit down. Log base 2. Same thing again. So do it again. Probability amplitudes go down, and the support broadens. And then, of course, the whole thing has changed position because the iterates in the support are moving around. Again, gone down by a factor of 2, broader by a factor of 2. Same thing again here, time 5. So part of what we see here is that because of the slope, the spreading, this peak distribution is now kind of spreading out, like in the dot spreading. Okay. Now something interesting happens from the 6th iterate. Anyone have a guess what's going on here?
It's doubling back on top of this as it switches out.
Yeah. So again, the way we have to think about how the iteration is working is we're, at each step, we're thinking about the range and who can contribute. Notice here at time 5, iterate 5, this distribution now actually sits across a half. It sits across a half. So that means there'll be some values of x where I get 2 contributions. So it looks a little odd. All of a sudden, this bump appears out of nowhere. No, it's an overlap. There are 2 contributions. One piece from here, one piece from here that go into this. And then from this point going forward, well, this is actually away from a half. It just broadens out. Okay, so the net effect is that the distribution just spreads out. And you can imagine if I did this more and more and more, it would just go to this homogeneous, flat, constant background, which is a little bit of a hint that maybe there's a notion of an attracting distribution at long times. It's plausible. I could have started this initial peaks distribution at different places, and it would still end up down here. So in the space of distributions, we can ask, are there sort of attracting distributions? Okay, let's keep going. It's a little bit more complicated than the shift map. We'll do the tent map. Now the tent map has slope 2 everywhere, and in particular what I'm taking. It has a control parameter a, but I'll set that to 2, so the map goes all the way to the top. And the only difference with the shift map is this upper piece has negative slope. But as you remember from the first way we described how we push distribution forward, it doesn't really matter what the sign of the slope is. It's just the stretching factor. The absolute value of the slope is what's important for how the probability amplitudes change with time. So this actually looks fairly similar. There's some differences in detail. Okay, support moves, amplitudes come down exactly the same way before, because it just doesn't matter. The distribution here is sitting right under just one of the monotone pieces, one of the other monotone pieces. Same thing, time 5, and then boom, time 6, something strange happens. So we do have another bump showing up, and that means that there's some part of this, well, it does actually have, the support does span both sides of a half, and then that means there'll be pieces that contribute, 2 pieces that will contribute to the range. And then there's also basically a region where there's no probability. That's where that upper value maps. This piece up here maps over here, and then there's no probability. And then keeps iterating on. So then we have another bump down here, means we have 2 contributions and so on. And the same comment about doing this again and again. It would eventually go to a uniform distribution.
Which makes sense from a slope being bigger than 1.
Yes, everywhere, right, exactly.
Yeah, a less than 1.
Right. Yes, I'll show you some examples of that. That's where the fun is. But this is the kind of ideal case. It just, and very quickly, because it's always, everything, the probability amplitudes are always going down by half each time, modulo this occasional kind of piling up and having multiple contributions. But those attenuate, and it just gets smaller and smaller. And so you can ask about, well, is there something we can say about the long time distribution? Imagine I had started, so if the long time distribution seems intuitive that it'll just be completely uniform, imagine I had started with that. Does that distribution come back to itself? Is there a notion of a fixed distribution, just like a fixed point? So we'll come back to that in the second part. But let's keep going on. So now the logistic map. Again, I'm taking r equal 4, so the map, like the others, always goes to the top of the interval. We can calculate the slope here, and we notice that the slope, it depends on where we are on the interval. So the slope is greater than 1 when x is less than 3/8 or greater than 5/8 over here and over here. So we'll have spreading. But then between those 2 values, the slope is actually less than 1, so we'll have some concentration of the probability. So this is just a more complicated case, more interesting case. Right? Depending upon where we start in the interval, we might have lots of spreading or some shrinking. So here's the consequence of that. So same initial distribution. Doesn't look too different, just maps over here. You can see there's a little bit of a slope up here, and that corresponds to the support here, the little piece of support moving across regions of the map that have slightly different slope. So it slightly modifies the probability amplitudes mapping forward, but just a little bit. Kind of curiously, the way I chose this example, after the second iteration, it comes back to exactly flat. I don't know why I did that. And then, oddly also for this case, the lower boundary of the support is actually right at a half. Okay, so now that's at time 2, this distribution is right under here, and we get to see. So what happens is that the lower part is a half, it's going to map to 1. And then we also have the slope at a half being 0 or very, very close to 0. So what happens is, and it's a little hard to see here, so we have this piece, this side mapping to 1, and right there we see that there's a spike. Let me point it out here. There's actually a spike right here. So it was broad. Now the support is now narrower. Right? I had a big piece here, but slope's going to 0. That's getting concentrated. In fact, concentrated so much, there's actually a kind of a square root spike here. And then 1 maps to 0. So this thing all maps down to here, carrying along the spike now. And then, since the distribution is concentrated down here in the regime where there's just a large slope, it's about 4 here, it just spreads out, and spreads out. So it spreads out, spreads out, and spreads out until we go from 5 to 6, the distribution goes over a half. And then we see these kinks again because now there are multiple contributions. So this distribution goes all the way over here. So that means there'll be values up here that get 2 contributions and we have a step. Now, also in this example, it's a bit curious with that initial condition. This, the next iteration completely goes away and we end up with this sort of 2 spikes, one at 0 and one at 1, and this smooth distribution. And if you keep going on, that just sits there. So this converges very quickly, and so there might also, for this case, be this notion of an attracting invariant distribution at long times. Still, well behaved. The difference with the previous maps is that we now have the density function having these spikes being very large. Well, these are the easy cases. There are also some fun cases. So just pick r equal 3.7, just a little bit below, so the map doesn't go all the way to the top. And here's what happens. So same thing we've already identified before. Support moves around. We see variation in the amplitudes because as the distribution broadens, the amplitudes are seeing parts of the map that have different slope until finally the distribution spans a half. That generates a spike. The spike kind of moves around. And now I just kind of jumped ahead because it actually takes a while for things to settle down, not like the previous case. It took exactly 8 iterations. As we keep going, here's at time 20. We end up with this very complicated distribution with all these sort of remnant images of the initial spike. Every time the distribution spans a half, it generates another spike and carries all the spikes around from previous times that the distribution got close. So we end up with, and this is sort of the generic case, a really complicated looking distribution with all these spikes in there.
Looks like density of states.
Oh yeah, it does kind of, yeah. 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 Yeah.
Which is probably, it's a similar thing happening with the band flat.
Yeah, right, exactly, right. You're just mapping, yeah, right, density of states, right, yeah. You're mapping a distribution forward, exactly. It's like a caustic or something, yeah. Okay, so before it was maybe, intuitive or plausible that we maybe talk about the distributions converging and becoming time invariant after many iterations. But those were simple functions, smooth, well-behaved, nice distributions. Here, whatever these putative long-term distributions are, or they can be quite complicated functions. This isn't continuous anymore. As soon as we get a spike in there, we have these discontinuities, which again is why we sometimes have to work with the distribution function for these continuous random variables. So. Okay, so now, how are we going to think about these long-time distributions? We just gave a bunch of examples. I kind of argued that it could be simple or complicated. There does seem to be this, in the space of distributions, some type of convergence, but how are we going to characterize this formally? And so we can work with it. So that brings in this notion of an invariant measure, or invariant probability density would be. Invariant measure here is just alluding to something we're not going to cover, which is measure theory, which is actually the more formal version of probability theory that you need to use when you work with these really complicated, non-differentiable, sometimes not continuous probability densities. But I'll just use the phrase invariant measure. You should think invariant probability density. Okay. So what could this thing be? It's some kind of distribution or density that maps onto itself, something like the analog in an invariant set. So, and we'd also like to know, are these things stable? So it turns out as we try to investigate these invariant measures, stability is a slightly subtle issue. I mean, what happens if I add a little bit of noise or change parameters? How much do these asymptotic distributions change? Are they robust or not? Okay, so what we're going to do here is define an invariant measure for just one-dimensional maps. So an invariant probability density, call it P star of X, is one that, first of all, the support is an invariant set. So at least the support has to be invariant, map into itself, right? So that's some set here. So we're guessing, okay, is this distribution P star invariant? Well, first we look at the support of it, right? All the X's that have positive probability, and then that set has to map into itself under the map. At least that. Now, more subtly, the probabilities are also invariant. They map into themselves, and we're going to use the Perron-Frobenius operator to define that. Right? Before, we were using it to iterate forward, and it was, in a sense, a dynamical system on distributions. Well, here's the analog of a fixed point for that operator. Right? We're looking for P stars such that when we plug it in to the Perron-Frobenius, it pops back out again. So this at least is a formal specification. Gives you some constraints of how you might search for such P stars. Or maybe if you guess one, then you could verify using this, that it was one of these invariant measures. So this is a functional equation. This fixed point equation is a constraint on the function that we're looking for, P star. So here's a real simple case, sort of familiar. Let's imagine that we had some periodic orbit, period K orbit. So how do I describe that? Well, its probability density is just going to be a series of spikes at each one of those values on the orbit, x1 up to xk. And I can write that down as a delta function of a product, x minus x1 times x minus x2, and so on. So that delta function will then place these spikes right there at the x1 to xk. And the question is this an invariant distribution? Well, okay, so we just had this formal specification, so we're looking for P. We just guessed, and when we want to calculate what happens at the next iterate, and then see if it's the same. So again, we just plug in here, which is what I've done. But the same argument as before. When we're following orbits, at least the math is the same. I have this function here that samples this function over here at x1 up to xk. So I end up with a delta function where I have the argument here is the product of those y's that are equal to f of the x1 up to xk. Well, what's f of xi? Well, that's the value at the next point along the orbit. So f of x1 would be x2, f of x2 would be x3, and then up to mod k. So I just actually do the iteration here, and I know since I defined it as periodic orbit that these map to each other under one iteration. And what is that? Oh, the result after I've kind of simplified this out and gotten rid of the mod here. Right. X of I plus 1, it doesn't really matter how I'm indexing, so I can just drop that. So I end up with this delta function of a product of y minus the x1, x2, x3, which is what we started with. So again, this is sort of a contorted way for proving the obvious, but at least it works. So in other words, we had these k spikes, and under one iteration, they kind of moved around each other, but came back to itself. So that's maybe a simple case, but at least how you can prove invariance. Here's a more interesting case, but also pretty simple. Let's look at the shift map again. And I kind of argued when we were looking at the example iterations that it looked like the map was taking that initial peak distribution to a flat one, so hypothesis. The uniform density on the interval is an invariant density. So I'll kind of go through kind of a graphical way of talking about that. So it's very handy. So I'm going to start off with my P0 being uniform here. It's handy to break this calculation of the next distribution into two pieces, namely where that part of the distribution that's under each of the monotone pieces. We'll do that separately. So that's this piece and this piece. Otherwise, I start with uniform. Should have colored it yellow. I break this into two pieces. Then I iterate forward this half distribution, one step, the lower half, and then the upper half, one step. Well, I just have uniform density here up to here, and then there's I just multiply it by 2, so the support goes 0 to a half. In the range, it goes 0 to 1 now, and it spread everything out and reduced the amplitudes by half. It started with amplitude 1, is now amplitude a half in the range. So we go from this in the half distribution to now this spreading out. This upper half, same thing happened here. Goes over the whole interval, but probably the amplitude is half. And now every point in the range has contributions from each of the one on the interval again, which is what we started with. You can do this with the Frobenius-Perron equation, 2 cases. It's essentially the same thing. Break it into these 2 separate calculations. Just move half of the distribution where the support is on 0 to a half or above a half. And we just plug in this distribution here, and now we're just integrating in the domain just from 0 to a half or a half to 1. The calculation is very straightforward because P0 is uniform over the x we're integrating over. And then we know what f of x is. Well, that's just 2x. That's what the map does over that part, slope 2. And then that's very easy to integrate. And we just get the value of a half out of that. And then same thing up here. All that's different are basically how we're integrating, because the map is still the same. So we get a half and a half, and then we add those 2 for each y. We add those 2 contributions up, and we get the half and a half. We get a uniform distribution again. Same sort of thing when we do the tent map. The case where it goes all the way up, a equal 2. The only difference here is that we have a negative slope, negative 2, but that doesn't really change anything. The first calculation we did for the shift map, this lower piece is exactly the same. So we get this contribution of a half everywhere in the range from this part of the distribution, 0 to a half in the domain. And then the only thing that's different here is that f of x up here is just 2 minus 2x, but you do the integral and it comes out to a half again. So the negative slope didn't make any difference here. So one more example and then one kind of an exercise. Tent map. So just showing you how to calculate these things in some tractable cases. So you remember the tent map, the bifurcation diagram, it also had band mergings. Turns out, so for the tent map, instead of setting a equal to 2 like we just did, we'll set a equal to square root of 2, and that's exactly where the 2 bands merge. We're going to guess a probability distribution here that has 2 pieces. Now I'm doing this with full foreknowledge of some of the dynamics. Turns out that there are 2 pieces, and the boundary between the 2 pieces is exactly a non-trivial, unstable period 1 orbit. It's a fixed point. The upper bound here is actually the iterate of the maximum. There can be no iterates that iterate above the maximum of the function, and then the lower boundary is the iterate of that. So what I'm going to do here is assume the distribution has these 2 pieces. The whole thing's normalized, and what I want to calculate are their probability amplitudes. So this is the guess here for the invariant distribution. Again, so x max is just a over 2, or in this case, square root of 2 over 2. The minimum value down here, just iterate this forward once, and then we know where this non-trivial fixed point is, the unstable one. And then we can just solve. We have, we want to find these 2 numbers, P0 and P1. So conservation of probability says that all of this stuff has to map into here, and all of this has to map into here on every iterate. Sometimes we call that noisy period 2. And then the other condition we have is normalization, that the sum of those together is 1. And you can just solve these 2 equations for P0 and P1. So we get an exact calculation of what those two values should be. And an interesting final case, which I won't go through the calculation, but it's part of one of the exercises, is a logistic map at r equal 4. I think I mentioned before. So folks back in at the Manhattan Project in the mid-40s were using digital computers, and they needed random number generators. So the John von Neumann, the mathematician, came up with using this logistic map as a random number generator. And he also back then noted this in very short abstract in the AMS proceedings, that this distribution was invariant. We saw that before. That was when r was equal to 4. We iterated down to that in just those 8 iterations. We saw those peaks. So we have these kind of square roots. So when x goes to 1 or x is 0, we have this kind of square root type divergence in the distribution. So you can see that here explicitly. If you like doing integrals, it's good to show that this is normalized. It's kind of simple, and pi shows up for bizarre reasons. And then you can also plug this guy into that Frobenius-Perron operator and show that it's invariant. Now the way you do it is through a coordinate change back to the shift map, and then you do the trivial integral. Well, this is how we do most integrals anyway. We try to make them make the integrand as simple as possible. So it turns out there's a conjugacy, and this is what the homework exercise is, a conjugacy that kind of steps you through going from the logistic map at r equal 4 back to the shift map, such that you can show that orbits of the shift map under this coordinate transformation become orbits of the logistic map. So in other words, you don't really end up doing a hard integral. You simplify the problem first. So, okay, so now some examples here. Maybe test our intuitions. Well, we just did this case. Okay, so 2 bands merged to 1. That was at square root of 2. And then what I'm going to show you is just start with some initial condition, iterate a whole bunch of times and make a histogram. So this is what you get, which is what we just calculated. So you have these 2 step functions. The boundary between the 2 pieces is right at that unstable fixed point. But now let's look at, quote, chaotic parameter values that are more complicated, 1.75, essentially arbitrary choice. So what happens there? Well, the height is larger. That's right, about 1.4. This is larger, so the attractor is actually bigger, but we see all these kind of stepping going on. At least we have some intuitions about why we're getting this stepping here, corresponding to the distribution making contributions from 2 different parts. And sort of an arbitrary chaotic parameter value for the tet map, we're going to have, in fact, an infinite number of steps. Not easy to describe analytically, like this case. Like essentially undescribable, but. Okay, so logistic map. So 2 bands merged to 1. So now this is sort of interesting here. So if you remember, we can calculate the parameter value r, where we get the 2 bands merging to 1. It's where the iterates of the maximum map right on to the unstable fixed point. And what we see is, I don't know, depending upon how you want to describe it, it's a pretty well-behaved function. There are only 3 peaks in it. And in fact, it's sort of like the tet map, the way I described it. This piece up here, one iteration maps down to here, and this piece in the next iteration maps to this. So there's a period 2 component, but then within the bands, it's random. And then at 3.7, well, I just showed you that, just to give the kind of visual contrast, the sort of, quote, typical parameter value, whereas chaotic, we get this very complicated set of spikes. So this is the analog to the tet map of having this many different steps. All these different spikes in there, which makes it hard to prove things in particular about this. But the real test will be this, the cusp map. So you remember the Lorenz max, Z max return map? And then our model of that was this map. It had 2 monotonic pieces to it, but then the slope went to infinity at a half. And here's a functional approximation of that Lorenz found. So now the question is, what's this invariant density going to look like? So the way I've drawn this, the slope is always greater than 1. Close to 1 down here, kind of goes into the identity that comes up. So slope greater than 1 means that there'll be a lot of spreading. So we should at least see, if we started even with peak distribution, some moderately quick sort of attraction down to this long-term distribution. It's spreading everywhere. Right? Small little concentrations are always going to get spread out and spread out and spread out. This distribution is just being spread out, spread out, and spread out at every step. What's going to happen here due to this? Slope is getting larger and larger and larger. It diverges here. That's a lot of spreading. Any small little concentration of probability mass is going to get spread way, way out. So anyone want to place any bets as to what the distribution looks like? Of course, you could have looked at the PDFs I put online last night, but it's extremely well-behaved distribution. It's very smooth. So that's the first puzzle. But not really, because like I said before, everything is spreading, right? The complicated distributions we just saw, the spikes, or the steps in the tent map, the spikes in the logistic map, those were all due to the slope going to 0 and taking probability mass and concentrating it, giving us, well, the square root singularities. Slope is always greater than 1 here. There's no concentration at all. And that leads to very well-behaved, smooth, continuous differentiable probability densities, asymptotic densities. I mean, it's a little bit, maybe kind of, at first, a little bit kind of puzzling. But, now, is it clear that the probability down at 0 is higher than up here? You can sort of see that by looking at the map. Well, imagine I just flop down here some iterate close to 0, because the slope is close to 1. I'm just going to kind of stay there. I'm just going to stay there, move very slowly, very slowly. I'll spend a lot of time there. In other words, the probability will be larger. Whereas up here, when I get up to 1, things are spreading out. So that's going to drop the probability density. So this is just a very, very well-behaved, smooth function. In fact, it keeps going down very smoothly to 0. So that's good. I mean, we have now a way of thinking about how distributions converge at long times, a way of formally specifying what it means to be being an invariant measure, an invariant distribution, the fixed point functions of the Perron-Frobenius operator. But it turns out there are a couple other technical issues if we want to work with invariant measures. I mean, one of the main reasons we're interested in invariant measures is if you want to calculate some statistic of a logistic map, tent map, or more complicated maps, if you have the invariant distribution, then you just do an integral. I want to know what the mean value is, or the deviation value. If I give you the invariant density, you can calculate that. So it's very handy. Characterizes many important properties of a chaotic system. But as we talked about before, even the shift map has periodic orbits in it. In fact, a countable infinity of periodic orbits. They're all unstable. And kind of the typical point you would pick on the interval and iterate, like 1 over pi as a starting point, that'll be aperiodic, but there still is a countable infinity of these periodic orbits, and every one of those things is associated with an invariant density, just like I proved. any periodic orbit, if I start the initial distribution as these spikes resting on the points on the periodic orbit, they're going to map into themselves. So this picture that we had, hopeful picture that, oh, in the space of distributions, we have a kind of dynamic and these attractors. So I was just giving you all the kind of positive cases. In this space of distributions, there are also a countable infinity of other invariant measures sitting on the periodic orbits. So if I just give you a map, one of the questions is, what would you actually see? Periodic orbit? All these delta spikes sitting there? Or do we see this other thing? Name of the ones I've been showing you. So one of the ways that you can sort of select out what's now called the natural measure in this, for any mapping like this, any dynamical system, there'll be an infinite number of invariant measures. And you'd like to know what's physically relevant. Well, what you can do is add a little bit of noise. So in each iteration, you add just a little bit of noise, arbitrarily small, and that will destabilize if the system is sitting on one of these invariant measures on a periodic orbit. Any small variation will knock it off, and then you'll start to see this so-called natural measures, the ones I was showing you, that fill out the full interval. And there's kind of a notion of robustness to these. You can also show that if you start on the invariant distributions and you add a little bit of noise and then let it go, it'll come back to those. So they are attracting and stable and robust in a sense. So that's it for today. Do you have any questions? So remember, we're going to shift again next time to start talking about sequences of measurements, orbits and trajectories, and how we use probability theory to describe distributions, not over the state space, but over sequences in the state space, which is in some ways kind of upping the ante and making a higher dimensional problem, but then that'll lead us directly into information theory as a way of grappling with some of that complicatedness. Okay, great. See you Tuesday.